Buenas tardes, Steven.
Buenas tardes, profe.
Se varía la funcionalidad de una sola molécula. Y bueno, en ese comentario estoy totalmente
Viendo
de
la...
acuerdo.
Escuchando la charla.
Ajá, sí, la parte de preguntas. Está interesante, ¿no?
Sí, estuvo muy bueno.
Eso lo que va a conducir es a diferentes fenómenos de transporte de carga, a una diferente conductancia. Entonces,
Profe,
una de las alternativas.
tengo una pregunta de la presentación. O sea, si hubo una mejora, digamos, visible entre utilizar las hojas de grafeno que las nanopartículas de oro, me parece que estaba utilizando como electrodo superior.
Sí.
¿Hubo una mejora visible en la conductividad o estaba más o menos lo mismo?
Lo que hacían era reproducir lo que obtuvieron con las nanopartículas encima de la película. Esencialmente no creo que haya mejorado, sino que era una alternativa, ¿no?
Ah, sí, porque se me hacía bastante parecida la conductividad de una con la otra.
Sí.
Sí. Y también justo se iba a preguntar si es que si es que hay alguna otra forma aparte de las nanopartículas. Lo que esta pregunta de los espaciadores más o menos.
Así, lo que yo he visto en ese contexto es que, fíjate que él tiene que cuando hace la técnica con grafeno, con nanopartículas, él abarca varias moléculas paralelas, ¿no? Entonces eso necesariamente se constituye como una especie de nanopartícula de moléculas, ¿no? Una nanoregión de moléculas, ¿no? Entonces ya se va diluyendo un poco la propiedad de una sola molécula, que es la que tú quieres capturar, ¿no? La miniaturización se pierde. Entonces, lo que yo he visto hacer en la literatura es que se usan espaciadores, se usan moléculas que uno sabe que no van a interactuar lateralmente con las moléculas objetivo, y entonces uno las deposita y deja como hoyos dentro de la superficie. Y en esos hoyos depositas la molécula que tú quieres usar como dispositivo. Y entonces él queda aislado, tú puedes depositar una sola molécula una sola nanopartícula encima de esa molécula y haces realmente un dispositivo a esa escala, pues, ¿no? Con todas las propiedades moleculares que tú quieres acceder. Entonces, eso también te permite, por ejemplo, depositar de manera orientada tu molécula, porque tú tienes algunas moléculas que cuando acercas a una superficie se acuestan y otras que se ponen de pie, ¿no? Y entonces, las moléculas que se acuestan, que muchas veces son las que nosotros queremos, ¿no? ¿Cómo haces tú para orientarlas verticalmente en la superficie? Entonces pones esas hormas y esas hormas orientan a la molécula en su deposición también, ¿no? Entonces tiene varias ventajas ese esquema.
Sí, estaba súper interesante esa parte.
De la interfaz entre la química y la física.
Sí. Un poco más experimental estaba viendo ahí cómo utilizar el STM.
Exacto. Si quisiéramos estamos armando nosotros en física un laboratorio de electrónica molecular. Precisamente con Henry tuvimos el año pasado un proyecto CEPRA y construimos un break junction en la universidad. Y entonces ahora nos toca un poco, ya obtuvimos algunos resultados con metales, simplemente rompimiento de juntas metálicas, y ahora para hacer un poco de electrónica molecular, una vez que podamos volver al campus.
Sí, es súper interesante. ¿Y qué equipo se necesitaría para eso?
¿No? Lo construimos completo. Necesitamos es esencialmente algo que se controla con un piezoeléctrico, y entonces con el piezoeléctrico tú haces esas retracciones, ¿no? Acercas una punta a la superficie, la retraes, acercas y la retraes repetidamente. Claro. Y entonces todo eso ya lo hicimos. Y entonces la electrónica en el entorno de eso tiene que ser una electrónica rápida y sensible para que perciban los regímenes de de tuneleo y entonces pueda entonces repetidas veces obtener los escalones de conductancia que son característicos de cada molécula que pones ahí. Entonces todo ese entorno ya lo tenemos y tenemos que más bien es ahora construir la celda donde está el líquido, porque todo esto es en fase líquida cuando haces electrónica molecular. Al ser en fase líquida, de manera de tener las moléculas suspendidas ahí, que entren en el contacto y se hagan las medidas, ¿no? Eso es la parte que falta y seleccionar un poco las moléculas que son más adecuadas para hacer la electrónica, ¿no?
Ah, claro, así es la parte de química, creo.
Exacto.
Un poco más.
Exacto. Tenemos un químico por ahí a quien consultar.
Sí, sí, el profe Edward mismo lo veía.
Exacto. Bueno. Muy bien, entonces vamos a empezar la clase. ¿Dónde quedamos ayer? Okay. Okay. Aquí tenemos la pizarra. Yes, so yesterday we started on a serious statement of the evolution of excess carriers inside a bulk of a semiconductor, right? So we started with these following equations. Okay, so these are balance equations for this the number of right-going positive carriers with respect to space, plus the generation rate, minus the recombination rate. Okay, so we derive that equation from a microscopic model. Okay, so this is the number density of total, okay, total positive carriers okay, and we had exactly the same equation for the negative carriers. What am I doing? X plus okay. So now we combine these equations with the equations we had derived for the current densities. So we had the current density for positive charges. Okay, combine. So the drift term and the diffusion term. Okay, and the same for the negative carriers. Yeah, E mu negative times negative E plus E dn dx. Okay, so these are the equations we derived previously, and then we use the fact that we combine them using the fact that J, the current density of the positive carriers, divided by the charge, the charge of those positive carriers is the definition of the Fp positive, and analogously we have the current density of the negative charges divided by the corresponding charge is the definition of Fn plus. Okay, So using these definitions, the relationship between current density and the number density, which is just mediated by the charge. So we substitute now these equations into the previous equations, and okay, and we massage that a bit and put this in terms of the excess charge. So remember that N is equal to it encompasses all the negative charge, right? So this will be the equilibrium negative charge plus the excess charge. And then we also have this for the positive charge. So we have P is going to be the equilibrium positive charge, okay, plus the excess. So this, remember that this was the excess carriers, okay? Okay, excess carriers, and these excess carriers are induced by perturbation, induced by a perturbation. Okay, so we will see now why these carriers are going to behave differently from, so you know that these carriers have associated a mobility. For example, this will be the mobility of the negative charges, and they have a diffusion constant, okay, which are the ones that appear in this equation. So this, in a sense, these factors here are going to be the microscopic or the equilibrium carrier properties, these mobility and diffusion constant, okay? But the excess carriers are going to behave in a different way because of many body effects, because of interactions. And we will see that because the equations are going to become nonlinear, and we're going to have to find the limit in which they are solvable, okay? So, so these carriers are going to behave according to some effective mobility and some effective diffusion constant, okay? So the next steps we're going to do is to turn the resulting equation, which I'm going to write in a second, into an equation for the diffusion and the mobilities of the excess carriers, okay? So, let me write the equations we arrived at last time, so we can start the derivation. So we have the equilibrium carrier positive diffusion constant, and then we could put this all in terms of the excess carriers. Okay. Minus P, and then I've developed this term because this will be part of the argument, so this will be N plus dN dx plus T d, okay, plus the generation of, sorry, N G, the generation of negative carriers, and the recombination rate, which we will write like this. N, and this was all equal to the time evolution. And this is the characteristic of this equations, rate equations, describing the excess carriers. Okay? So this is my equation. So this again, I made a mistake here. This is going to be N diffusion constant. Okay? So this is the negative charge equation, and we have an analogous one for the positive carrier equation. There's a difference in sign here, so we have to put, and this is again N. Okay, and this would be the positive one. So you see that there's a complete correspondence between the two, except for some signs. For example, this is sign difference there because of the charge. And then we have plus G minus P over P. Right? Okay, so these are the two main equations. So here we have made no approximations until now. Okay. Remember, we have in our minds this approximation of low injection rate and the fact that we have either an N-type or P-type semiconductor. So there's some approximations here that we want to do. So we will incorporate into these equations in order to simplify. And we'll see later an example of how well these approximations work. So we will incorporate the low injection limit. Okay, and the low injection limit is that the generated number density of excess carriers will be much smaller than N0. Okay, this is in the case of the excess that we have an N-type semiconductor, and of course, if we have an N-type semiconductor, we will have that the equilibrium number of negative carriers is much larger than the equilibrium density of positive carriers. Okay, or N-type. Okay, of course, you can have also in the case of P-type, you have then that this is going to be much smaller than the equilibrium density of positive carriers, and then you have that P0 is going to be much larger than N0 or P-type. Okay, so we want to incorporate that approximation here. We will not do it immediately, but this is one limit in which we want to work these equations. And the other thing, the other physics we want to incorporate is ambipolar physics. Okay. Need to include. Okay, why do we need to include this? Because this implies a dependence, and a dependence which is not incorporated in the previous equations between delta N and delta P. Okay, and this happens due to a phenomenon that we already saw in the case of a gradient of impurities. Okay, so what's going on? Let's see the whole physical scenario here. So we have again the valence and conduction bands. Okay, and let's suppose we apply an external electric field here. Okay. We apply an external electric field, and we have a certain concentration of negative and positive charges. Okay, then we apply. Let's see, do this with a little color. So we, for example, shine upon the material some photons. Okay. Then we're going to generate an excess carriers, because these photons, okay, now make for some transitions between between the valence and conduction bands. So now we get a concentration here of excess carriers in the negative and excess carriers in the valence band. Okay. So these so now we have this excess carriers, and this is what we call the total negative carrier concentration and the total positive carrier concentration. Okay. But what happens to these negative charges that are here and the positive charges that are here in excess, okay, when I have this external electric field? Put it here with a green. Okay, so let's suppose we put it here with an external electric field here. Okay, so the negative charges are going to move this way, and the positive charges are going to move this way. Okay, so again, this is going to generate a polarization of the material, because now we're going to, so this excess positive charges, put it here, are going to move this way, and the negatives are going to move the other way. Okay, and this will generate an electric field, an internal, an induced electric field. Okay, this induced electric field will not let these charges go too far away. So there's a dipole moment here that is induced just because the charges are moving, and eventually this electric field sort of forces the charges to move together in a single direction. Okay. Okay, so this is the correlation between the motion of the two charges, okay, due to this induced electric field. Okay, is it clear? So that means that we have to introduce this physics into the previous equations, which was not taken into account. We have not accounted for this induced field. We might do it. For example, we might do it. We're not going to do it that way, but we might include, if we want to do really detailed, in case of, you know, the experiments are not according to a theory, one way we might go in order to incorporate this physics is to include the Poisson-Boltzmann, Poisson equation, sorry. Poisson. Okay, so the Poisson equation, what does it tell me? It gives me that the general form is just this equation. Okay, the divergence of the electric field is the induced charge, okay, or the free charge, okay, and the free charge is going to be E times delta P minus delta N, okay? And remember, these have spatial dependencies over the dielectric constant of the semiconductor, okay? And this is equal to the induced field, the gradient of the field, dx. So this is the one-dimensional version of the gradient. So this is the Poisson equation, okay? So we might calculate this in this way, but we're going to assume, okay, so this will complicate. Now we would have three coupled equations to solve for the whole thing. So what we're going to do is the simplification to incorporate, okay, the simplification to incorporate this effect is to do an extreme case, is to contemplate an extreme case. We're going to assume that delta P follows delta n in time and space. So that is, we are assuming that this internal field is so strong once it's generated by the external field. So this external field is going to be relatively a perturbative field, okay? So a linear field. And this will separate, and the internal field generated so strong that it keeps these charges together all the time. Otherwise, we would have to have a diffusion constant for the excess negative charge and a diffusion constant for the excess positive charge. So this will be a really complicated problem, because now these wander about, okay, finding the different obstacles and scattering centers, and these wander about separately, okay? So this induced field is so strong that it keeps these two charges together. So we always have delta n is delta p in space and time. Okay, so we believe that this is the result of an extreme case of an induced field here. So this is zero always, okay? So the gradient of the induced field is zero. And this we will see how it comes about in the equation, okay? So, so what are we implying by this? So if delta n and delta p are the same always in time and space, we have that the generation rates are the same for p and n, and we have that the recombination rates are the same for negatives and positives. Okay, let me put it like this. Okay, and we will name this then a single regeneration rate, and I will name this a single generation rate. Okay, so as they move together, they will recombine and be generated together also. This is what it means. Okay, and so we will not have a separate generation and regeneration rate, generation and recombination rate for both charges. Okay, so if we incorporate this into the previous equation, so let me write, for example, we have to write the two equations so we see that what's happening. So we have that the partial of delta n, delta t, is going to be equal to, and this is the equation for the p, okay? So I already substituted delta n, right? So delta n for delta p in this equation. So this first equation. Here we still preserve the microscopic or the thermal diffusion constant with its own type of carrier, okay? But I'm substituting everything that's delta p for delta n. So everything is delta n now, okay? Delta n squared minus mu p. Notice that this is the equation for p, so I have the mobilities also for the thermal carriers, okay? And then we have the field delta n delta x plus the electric field, and I'll tell you in a second why I put p there. Okay, so P in the previous section, I cannot, this is not saying that delta n is equal to delta P does not imply, okay, that P is equal to N. Remember that P includes P0, okay, and N includes N0. And these need not be, especially if you have an extrinsic semiconductor, this can be much larger than this one. So this, okay, does not mean that this is equal. So only the excess carriers are going to be equal, okay? So that's why I leave P here, okay? And then we have the generation rate minus the combination rate, okay? That's a full equation. One second, I have to plug in my computer. Okay, so that's the first equation. And my second equation will be the equation again in terms of the, this will be the n equation, okay? That was already in terms of the excess carriers, but now I have here the n diffusion constant, second derivative, delta n x, plus, okay, this is E times delta n, so these terms are exactly the same except for the mobility. So now I have here now the negative total density, gradient of the electric field, okay, plus G minus R. Okay, so now we have the two equations, then we have effectively incorporated the fact that now delta n and delta p are behaving exactly the same time, exactly the same way in time and space by incorporating the only the delta n in the equation of motion. So this is how we couple. This is a coupling, the ambipolar coupling. Okay, ambipolar coupling. This is how we incorporate this. Okay. Now I'm going to multiply this in order to obtain a single equation from these two, because this describes both the evolution of delta n. I'm going to multiply the first equation by mu n times n, okay? And the second equation I'm going to multiply by mu p, okay? And you see that mu p and mu n are different, okay? They're independent. They're sort of they're the thermal mobilities. Okay, we multiply these two equations, and we're going to subtract them. Okay, subtract. Okay, so if we subtract these two equations, we're going to see that the mu n, so we're going to have a time derivative here. Yes, okay, so we're going to have mu n times n, mu p times p times this, so we factor the time derivative here, okay, multiplied by these coefficients, so being subtracted, okay, and then we have the corresponding, now we can factor also this gradient of the excess carriers, excess negative carriers, having some prefactor between the diffusion constants and the mobility, so the thermal diffusion constants and the thermal mobilities, okay? And then we'll have some combinations of these factors. Here, this will be trivial. What we obtain here, notice that if we multiply by these combinations, we have mu n, n, times mu p, times p. And then we have mu p, p, mu n times n. So these, this factor here disappears. So we eliminate, by this, subtracting both equations, we eliminate any dependence on the gradient of the electric field. Okay? Here we have NP Okay, here we have Pn, okay, and we have mu P, mu N, and here we have mu N, mu P. This has so we don't subtract, let's see. No, we don't subtract, so we add both equations. Sorry about that, and add both equations. Okay, so we add equations. Already we have the minus sign that would eliminate, and the rest of the equation is yields the particular factors. Okay, so let's see what the end result of this will be. So we have a single equation now for both excess carriers, right? So we have mu n times dp, okay, plus mu p dn, okay, and we have a second derivative of delta n plus, now we have this combination here, mu n, mu p minus n, and we have the external electric field here times the excess negative carriers, okay, plus now mu n plus mu p, okay, g minus r, which is a common factor in both equations, and this will be in terms of this combination mu n n is mu p derivative delta n delta p. Okay, so it's very easy to do the algebra. Just work this out. Add these two equations, and you'll see. So these two should yield a summation of these prefactors, as we have the same derivative, and then we should have here a combination of the mobilities and the diffusion constant that will result in a combination like this. Okay. And so on, okay? And we eliminate this. There won't appear any gradients because we just multiply these equations so that we eliminated the effect of the gradient. Okay, and this is the single equation that is going to describe a ambipolar transport. We just have to simplify this a bit. Let's divide this whole equation. As you see, I'm trying to make this equation look exactly the same as one of these equations. So you see, here we have a derivative, time derivative without any coefficient, right? Here we have a second derivative multiplying only a diffusion constant, okay? And here we have a first derivative multiplied by the field, multiplied by a mobility. So if we set up the next equation in the same way as this equation, we can identify an effective mobility. So what do we have to do? An effective mobility and diffusion constant. We have to eliminate whatever factor is in front of the time derivative so that we recuperate the same form of the equation. Okay? Is that clear? So what do we have to do here? We have this coefficient here, so we have to divide the whole equation by that coefficient. So let's do that. This is a very sneaky way of obtaining the physics of the excess carriers. So we have now this coefficient here, and we divide by mu n n plus mu p. Okay, and this will be multiplying the second derivative. Okay, then we also have a dividing factor of this coefficient here, p minus n e. So let me separate that e, so it's not part. Remember that this is the part of the form of the equation. Okay, and this will be divided by mu n. Let me do that a little better. Okay, divided by mu n plus mu p. Okay, times this factor, then we have, okay, when we divide by this term, this is exactly this term, so we get just the generation and the recombination rates here, and on the other side we get this equation. So you see that this has exactly the same form of a drift diffusion equation. Okay, so we can identify, so it has exactly the same form as the original drift diffusion equation. No coefficient here, diffusion coefficient in front of the second derivative, and the mobility in front of the first derivative in space. No coefficients in front of the generation recombination rates, okay? So we have exactly that same form. So this is going to be now my effective diffusion coefficient for these excess carriers, and this is going to be now my excess carrier mobilities. Okay, so excess carrier diffusion. Okay, and this incorporates the physics both of the thermal diffusion constants, okay, and the physics of the ambipolar transport, both incorporated into a single unit, okay? So this is what I call d prime, and this I call the mu prime, okay? Okay, so any questions here? Let me write those two equations cleanly here, that d prime, okay, diffusion constant. So if we generate additional carriers by any means, by some external perturbation, they're not going to behave in the same way as the thermal carriers, but they're going to behave through this effective diffusion coefficient, okay? Diffusion of excess carriers. Okay, remember that, look, as far as this equation goes, this is only the description of the excess negative carriers, which is the same as that of the positive carriers, okay? Only, so this will be the diffusion of those carriers only, okay? It doesn't involve the equilibrium carriers, okay? So this will be then equal to mu n dp plus up p dn divided by mu n plus mu p. Okay. Remember again, here we don't have delta n because the fact that delta n is equal to delta p does not imply, okay, does not imply that p is equal to n. Okay, because these P and N incorporate the equilibrium densities, and the equilibrium densities can be far away from each other. Okay, so this would be the effective diffusion constant for the excess carriers, and here we will have then mu P, okay, P minus N over this combination. Okay. Notice it doesn't include the E here because the part of taking this equation into the same form as the previous equation involves incorporating this electric field here. So anything besides the electric field here is incorporated into the mobility. Okay. So these are the effective the effective diffusion and mobility. One problem left over from this, and this is a giveaway, okay? What gives away that we have interactions in the problem. Okay, well, what gives it away is that notice here that this P is incorporating a delta P, which is a delta N, okay? And this then makes for a nonlinear equation again. You see that although we have incorporated here the D prime, the diffusion coefficient, this D prime depends on the total concentration of positive and the total concentration of negative charges. And if we separate this delta, this N into N0 plus delta N, we get a quadratic, a quadratic dependence here. Now a nonlinear dependence in the equation of motion, in the differential equation. Okay. The same here. We have delta N, and here we have a delta N and a delta N here. Okay. So we get again a nonlinear dependence here. So this what gives away that we have interactions. Okay. Nonlinear equation. Okay. So this is a big point that we make here, and that will sort of will give us the direction in which to go next, in which to apply the remaining physics that we haven't applied to this limit. Okay, which is incorporate the low injection limit. Okay, in an extrinsic type. Okay, so how do we get rid? Okay, in general, nonlinear equations are horribly difficult to solve. Okay, so what you do generally is we did this before, is to linearize. How do we get rid of nonlinearity? Okay, and we're going to get rid of nonlinearity not by any trick. We cannot get rid of the nonlinearity by any mathematical trick. Okay, using physics. Okay, so we're going to explore a limit. Okay, we explore a limit. Explore a useful limit in which what happened there? Small delay in which the equations are linear. Okay, and linear equations we know how to solve up and down. So let's say so I was claiming before that this useful limit was the low injection limit. Okay, this low injection limit means that delta n is going to be much smaller than either P or N0, okay? And that for a P-type semiconductor, okay, we have that P is going to be much larger than N, and for an N-type, you're going to have N0 much larger than P, okay? Notice that as we have a single equation now, we have a single equation here, we have to apply those conditions both to the coefficients, so we're going to expand now N and P, okay? And incorporate those inequalities that I have here into the coefficients. Okay. So let's do that, and we'll find something really nice as a limit. So let's start with the diffusion, the effective diffusion constant. So we write it. I'm going to start from an equation I will ask you to derive. So another way to write the effective diffusion constant is going to be like this. Okay, so this is just massaging the previous equation we had. Okay, so the previous equation we had is this one. Okay, so one thing that I am going to ask in the next homework is to show that this equation is exactly the same as this equation here. Okay, so this is a more simplified version that is going to be simpler to apply this conditions of low injection. Okay, so let's apply now that n, what are the n and p in terms of the excess carrier. So this will be the n dp, okay? So this will be times n0 plus delta n plus p0 plus delta n, okay? And here we will have dn n0 plus delta n plus d p0 plus delta n. Remember, anytime we have a delta, it will be the same for p's and n's. So I just put delta n for all the excess carriers, okay? Okay, so now we can, if we have, for example, let's say we have to apply we have to apply a particular type of semiconductor. So we have a p-type, okay? So we have that P0 is going to be much larger than N0, okay? And we have that delta N is going to be much smaller than P0, okay? So we apply that to this one. So we have that the P0, so we neglect this N0 in front of P, and then we neglect the two delta N's in front of P, so we get just this simple expression here, dN P times P0. Okay, that's in the numerator. And then we have also the delta N in the low injection rate will be much smaller than this one. And the delta N will be also much smaller than this one. And P0 is going to be much larger than P. Then P0 is going to be much larger than N0 because of this limit. Okay. Okay, so we get now in the denominator, we will just get the dp p0. Okay, and this is it. Let me take care of aesthetics a bit. Okay, And here we have that these guys are going to cancel, these guys are going to cancel. And you see that this is a very nice limit because the effective diffusion of the excess carriers is going to be what? The diffusion constant of minority carrier. You see why I call this minority carrier? Because this is a p-type. So the majority carriers are going to be p-types, okay? In this case, they're going to be majority holes, okay? But the diffusion constant is given, the effective diffusion constant of the excess carriers is going to be the minority carrier, okay? And now this is a constant. This is another thing, constant. Okay, it doesn't depend on the densities like the previous expression, okay? So now if we reduce the diffusion coefficient, the effective diffusion, in terms of something that is carrier density independent, then we have a linear equation, okay? If these coefficients here are now independent, okay, of the carrier densities, then this turns into a linear equation and we're in business, okay? Let's see what happens to the mobility, okay? So the mobility mu prime is going to be equal to mu n times mu p, and we have p, so this is going to be p0 plus delta n, minus, and then there's a minus sign now here, it's going to be n0 plus delta n. This is divided by, then the same combination, but now with the mobilities instead of the diffusion constants. So we have delta n plus mu p, p0 plus delta n. Okay? I don't need this final brace here. And this again, okay, so you can see very easily that if we're in a p-type, so this is the dominant factor here, so this will be much larger than n, so we neglect it in front of that, and then p0 will be much larger than, and here even it's simpler because the delta n's cancel here, okay? So we just have to compare p0 with n0 in the low injection limit, and we get mu n times mu p times p0 in the numerator, and then we get in the denominator mu p times p0, okay? So this gets cancelled, and this again corresponds to the mobility of the minority carriers. Okay? So you see this? Is it clear? Do you have any questions? So this is really a really nice limit. It's a relevantly a physically relevant limit, the low injection limit. Okay, and it turns our equations into a linear equation. So now we're in business. Okay, so for a p-type, let me conclude. So for a p-type semiconductor, you have a p-type. Okay, you have the equation of motion of excess carriers is going to be this equation. Minority carrier diffusion constant, minority carrier mobility, okay? This is going to be my equation. A linear equation. Okay. Okay, so we know how to solve, we learned how to solve these equations since we were in Common Core, so we just apply those techniques and we can solve for any conditions that for which we know, at least all the techniques we know for second order differential equations. We know not all the second order differential equations have known solutions, but generally that the conditions that we have in semiconductor physics, we're going to be able to obtain a solution. Okay. So I'm going to leave for you to solve the n-type. In the n-type, you obtain some new features, which are, for example, well, this is not a new feature, T prime, of course, is the minority carrier diffusion. But you obtain something peculiar, which is the minority mobility is negative of the minority mobility. Okay. Okay. So this is easy to solve. So I leave this for the homework. Okay. And you can solve for that. Any questions up to this point? Make some signals that you're there, that you're attending the class.
So one question.
Yes.
Last part is already included in the homework, or is something extra?
No, I will include in the homework.
Okay.
Okay. Yeah. Okay. Okay. So now let's do an exercise here to see what the physical scenarios are, and this is one experiment that Werner will do. I don't know if he will do it with you in the labs, if we ever return to the labs, or he will do it in a demonstrated fashion. Okay, so this will be the Haynes-Shockley experiment. Okay, so let's do the math associated with this experiment using this previous equation. Okay, so the scenario is the following. I have a chunk of material. Okay, for example, I have here 2 electrodes. See if I can use some should start using some of the thing is that the things get in the way when I try to here. Let's see. One rectangle, right? And I have another rectangle here. Okay, and then we put a couple of lines here. So we have here a semiconductor. Okay, so let's suppose this is a n-type. Okay. Go back to my pen. How do I go back to? Yeah. Okay. So this is an n-type semiconductor. Okay, and I'm going to apply an electric field in this direction. Okay. So this is an n-type semiconductor. So I apply an electric field, and then I'm going to introduce. Let me use another color here. So I'm going to introduce an excess carriers into the semiconductor. And Werner will tell you how to do this. Okay, so I introduce an excess delta n here, and I'm going to see how this excess carriers evolve in the system. Okay. Okay, so mathematically, from the experimental point of view, I will introduce like a pulse like this of excess carriers, and then I'll see how this pulse evolves in time. Okay, introduce a pulse. Of excess carriers and work out the evolution. Okay, so let's see how this works. So we start from the n-type equation. The n-type equation, FEP, okay, minus mu p. So from the mathematical point of view, it's easier to solve the equation if we introduce a delta pulse instead of a square wave as I drew there, and that's what you have to do in nature. Okay, with a delta function. Perturbation. Okay, so we introduce the delta function. So this will be just a peak here, and we see a peak like this, and we see how this evolves in time. Okay, and we'll see also our solution should converge to a delta for time equals to 0. So we introduce a delta at t equals to 0, and after at t equals to 0, and okay, afterwards no more. Okay, no more g. So this, notice here I haven't introduced the g, right? So this is the r term, this is the recombination, and there's no g because beyond this describes what happens, what is going on after I introduce a pulse. The pulse is only introduced at t equals to 0, and after that there's no more g, so no more g in this equation. Okay, so this is how I introduce that example. Okay, so now how do we solve this equation? So we propose a solution of this form. We propose a solution. You saw how to solve these equations in mathematical methods 1 and 2, and maybe in the common core courses also. So we propose a solution of this form. So we're going to call this delta n prime, okay? And this is going to be a function of x and t, okay? And then we have an exponential dependence. This exponential dependence is suggested by the fact that we have this term here, okay? So this initial form, and I'm going to propose another one, another form for this n prime, is because we want to eliminate this term from this first equation, okay? Okay, so we substitute this form into the equation, and we get e to the minus t over tau p the left-hand side of the equation does not depend on time, so all the time dependence related to the exponential is factored out, okay? We have n prime dx squared minus mu p e0 dn prime dt dx, okay, times e to the minus t over t0 tp, okay? Mu, yes, minus n prime e to the minus t over tau p over the relaxation time, positive carriers, and on the other side we have 1 over, we have two terms because the right hand side has a derivative here with respect to time, and the proposed solution has time dependence here and in the exponential. So we get one, the first term is going to be tau p n prime e to the minus t over tau p. And then we have another term which is e to the minus t over tau p. Okay, dn dt. Okay, so you see now the benefit of separating this time dependence in the exponential, because this term is identical to this term here, so this gets cancelled. Okay, and we obtain a little simpler equation now to solve. So we get dp second derivative. You see we can cancel all the exponentials that occur all over the place here, so we cancel those exponentials there, and we get this equation. Okay, is equal to dn prime. Okay, so this is sorry, I made a mistake here. This should be a spatial derivative. Okay, so now this is a differential equation, a partial differential equation. It has both spatial and time dependencies. So for example, one of the methods we used in the previous courses in order to solve this is to assume that this is a factor of two functions, okay? One that depends on t and one that depends on x, okay? So you can separate this, this equation in the usual way, right? So you substitute the solution into here. We obtain on one side an equation of only spatial dependence, and the other side an equation only of time dependence, and they should both be equal to a constant, okay? And then we solve the equations separately, and then we multiply them according to this proposed solution, okay? So, I mean, I leave you to that particular exercise for you to do, looking through your notes of previous courses, and the final solution. Okay, let me put here the dependencies of time and space. Okay, is going to be then some constant alpha. Okay, for dp t square root. Okay, it's going to be a Gaussian, strangely enough, but this is the general solution, a generic solution for the diffusion equation. Okay, so we get x minus mu p times e0. Okay, And now the solution, now we combine this with the previous solution. Remember that n prime was part of the solution only. It involves also this exponential here. So we have that the delta and the excess carriers will be this n prime times the exponential of t over tau. Okay? And then the full solution would be alpha times this exponential. Okay? Over 4 pi dp. Okay, there's a square here. Okay, so minus x minus mu p 0 t square. Okay, so this is a quite easy one. If you're familiar with the Gaussian, it's very easy to interpret this this behavior here. We're going to separate this behavior from this behavior. We know what an exponential behavior looks like, but this Gaussian, remember that the Gaussian form is e to the minus. Then you have some, let's suppose some variable here, y squared over 2 sigma squared, okay? And then your standard normalization is going to be 2 pi sigma squared, okay? So from here, and what's this sigma? So the Gaussian is something, a form like this, okay? Now it's Gaussian there. Okay, so this, the width of the Gaussian at half height is going to be sigma. Okay, this is the x direction. Okay, and this term here is going to be the motion of the average of the maximum. This is the same as the average here, the maximum here. So this is going to move according to this peak is going to move according to this combination here, and this width is going to move according to this combination here. So let's extract the sigma, okay? So sigma squared is going to be 2 dpt, okay? So that means that sigma, the width of this curve, is going to move like square root of 2 dp. Okay, so this basically is describing diffusion, okay, and then the whole peak is moving like mu p d0. Okay, so we have the full scenario there. We have a Gaussian that is moving to the right, linear in time. Okay, so it's drifting to the right. Okay, and then the width of the Gaussian is increasing like the square root of t. This is a very nice scenario here. So we have, let's draw here in some this is a bummer here. No, it's going to have to go through another route. Let's see. Through here. Okay, let's make this straight line. So we here. Okay, so we have our first, and then we rotate this. Must be a way to engage this at a perpendicular angle. And we draw the other line. Okay, so we have a Gaussian we have first a delta function, right, at t equals 0. We have a peak at delta t equals 0. Let me draw that again. Okay, so we have a delta function here, t equals to 0. This is the concentration. Okay, this is time. This is time. Okay, so we have now at larger times we have a Gaussian distribution like this, and then it will spread out like this. Okay, and here I've incorporated also the fact that we have an exponential factor. So that's not the only part of the evolution. We have a Gaussian that is spreading out. Okay, and we get this prefactor that tells me that the amplitude is going to get reduced again as the inverse of the square root of time. But then we also multiply it by this exponential function. Okay, so we get a reduced amplitude for the Gaussian as a function of time. So let me put here time t1 and time t2. So that's what's going to happen to the evolution of the excess carriers as a function of time. So in the previous drawing that I did, I'm going to go back to that one. What you do experimentally is that you put a probe here, okay? You put a probe of charge, okay? So part of the charge that's being that moves along the semiconductor, you can perceive it as a function of time. So you should see the evolution in time. If you probe the voltage here, okay? You probe the voltage here, you should see the pulse of current going through the system. So you should see, for example, if you have your probe here, let's put the probe here. Okay, probe, voltage probe. Okay, so you should see a low current, the excess carrier density, then it increases and decreases. And you can prove how good these equations are by using this Haynes-Shockley experiment. Okay. Okay, so any questions about this? Let me just put the sorry?
I said no.
Okay, no. This is how this this average is moving, function of time, and how the width, okay, the width of the Gaussian is moving like to, okay. So it's much lower. The increase of this width is much lower than the motion of the wave packet. This moves like the square root of t, and this evolves. So this is essentially drifting here, drift, and this is diffusion. Okay. Okay, so this is all I wanted to tell you about today. I'm going to talk about an additional topic here, and then we'll go to the next chapter of the book, which is the p-n junction directly. Now we're going to start with some applications, real life applications of the equations we have derived. Okay. Any questions or comments? So let's say, what do you think about the turning in of the next homework by Thursday next week? Second homework?
Sorry, what did you say?
So what do you think about turning homework number 2 in by next Thursday? I hope to correct this first homework this weekend, and so that you can have your grades by and we can make clarifications with respect to the questions of the first homework in the Tuesday session. Tuesday session? No. Well, we can
Wednesday?
try. We can try to activate the Tuesday session with Berna. So let's see if we can have a session on Tuesday mornings to clarify the questions of the homework, and you can turn in homework 2 by Thursday. What do you think about that? Proposal. Okay. Homework 1 corrected by Tuesday. Homework 2 due Thursday. Okay.
We are talking in WhatsApp to discuss if this is okay, because we don't know if some people have done anything on the homework yet, or they are waiting.
Yeah. No. Okay. So think about it, and we can discuss it a little further. But in principle, let's put these due dates, and then we'll discuss it during the weekend, and we'll set the new due date we discuss next week. Okay. Okay. So very good. Okay. So see you next week then. Unless you have any questions, comments. No. Okay, so see you next week then. Keep safe.
To
See you. Okay, happy weekend. Bye.
Bye.